Tonight, we're going to explore something that will fundamentally change how you see reality itself. Not space, not time, but the invisible fabric that makes everything in the universe possible. Because here's what most people never learn. The chair you're sitting on, the air you're breathing, the light hitting your eyes right now, none of it works the way you think it does. There are no tiny solid balls of matter bouncing around inside your atoms. Instead, everything you see, touch, and feel is made from something far stranger. Fields. Invisible, omnipresent fields that stretch across every inch of the universe, from the space between your fingers to the void between galaxies. And even the emptiest vacuum in existence is humming with their activity. Before we dive in, if you find these kinds of deep explorations fascinating, a quick like or subscribe genuinely helps this channel keep going. It's a small thing, but it means the world to me. Now, let's begin. Let's start with something you do every single day without thinking about it. You touch things. You pick up a coffee mug. You sit in a chair. You feel the ground beneath your feet. These interactions feel solid. They feel real. When you knock on a wooden table, it resists your hand. It pushes back. There's a firmness to it that seems undeniable. Wood is solid. Metal is solid. The floor beneath you is solid. Your entire experience of the physical world is built on this feeling of solidity, of things being made of stuff. Hard, tangible, reliable stuff that takes up space and holds its shape. This feeling is so fundamental to how we experience reality that for most of human history, nobody questioned it. Matter was matter. Stuff was stuff. The ground was solid because it was made of solid things. A rock was hard because the material inside it was hard. This seemed obvious. It seemed like the most basic truth about the universe. And for thousands of years, the only real question was what that stuff was actually made of at the deepest possible level. What were the ultimate building blocks? What was the smallest piece of matter you could get? The ancient Greeks were among the first to seriously think about this. Around 450 years before the Common Era, a philosopher named Leucippus and his student Democritus proposed something radical. They suggested that if you took any piece of matter and kept cutting it in half, over and over again, eventually you would reach a point where you couldn't cut any further. You would arrive at the smallest possible piece of matter. They called these pieces atomos, which means uncuttable in Greek. These atoms, they proposed, were tiny, solid, indivisible particles. Everything in the world was made of them. Different arrangements of these tiny solid balls created different substances. Water was made of smooth, round atoms that could flow past each other easily. Iron was made of atoms with hooks and rough edges that locked together tightly. Fire was made of sharp, spiky atoms, which is why it hurt to touch. Now, by modern standards, a lot of these specific ideas were wrong. But the core insight was profound. The idea that matter is made of tiny discrete units rather than being infinitely divisible. That idea turned out to be remarkably close to the truth. It just took about 2,300 years for anyone to prove it. For most of those 2,300 years, the atomic idea was actually unpopular. Aristotle, who came after Democritus and was far more influential, rejected the idea of atoms entirely. Aristotle believed matter was continuous and made of 4 fundamental elements: earth, water, air, and fire. Different substances were different mixtures of these 4 elements. A piece of wood contained mostly earth and fire, which is why it was solid but could burn. Water was pure water element. Steam was water mixed with air. Aristotle's view, dominated Western thought for nearly 2 millennia, largely because Aristotle was so widely respected, and because the Catholic Church adopted his framework as compatible with their theology. For close to 2,000 years, questioning this view was not just scientifically unpopular, it was culturally dangerous. It wasn't until the early 1800s that atomic theory started to come back. An English chemist named John Dalton noticed something remarkable about how chemicals combined. When hydrogen and oxygen combined to form water, they always did so in the same ratio by weight. Always, without exception. No matter how much water you made, the ratio was the same. Dalton realized this made perfect sense if matter was made of discrete atoms. If one atom of oxygen always combined with 2 atoms of hydrogen, you would always get the same ratio by weight. His ideas, first developed around 1803 and formally published in 1808 in his book A New System of Chemical Philosophy, revived the ancient Greek idea of atoms but put it on a scientific foundation for the first time. Atoms were real. They had specific weights. They combined in fixed ratios, and they were the smallest units of chemical elements. But here's what everyone still assumed. Atoms were solid. They were tiny balls of matter, the smallest possible pieces of stuff. You couldn't break them apart. They were the bedrock of reality, indivisible, fundamental, solid little spheres, just as Democritus had imagined more than 2,000 years earlier. The modern version was more sophisticated, backed by chemical experiments and precise measurements, but the basic picture was the same: tiny, solid, uncuttable balls. That assumption held for almost 100 years. Then it shattered. In 1897, a British physicist named Joseph John Thomson was experimenting with cathode rays. These were mysterious beams that appeared when you ran electricity through a glass tube with most of the air pumped out. The rays traveled from one end of the tube to the other, and they could be deflected by electric and magnetic fields. Thomson carefully measured how much they were deflected and discovered something extraordinary. These rays were actually streams of tiny particles far smaller than any atom. He had discovered the electron, and this was a shock. If atoms contained even smaller particles inside them, then atoms weren't indivisible after all. They had internal structure. They were made of parts. The uncuttable could be cut. Thomson proposed a model of the atom that made sense given what he knew. He imagined the atom as a sphere of positive charge with the electrons embedded in it, like raisins in a pudding. This became known as the plum pudding model. The positive charge was spread evenly throughout the atom, and the negatively charged electrons sat inside it, held in place by electrical attraction. The atom was still fundamentally solid in this picture. It was a ball of charged stuff with smaller charged bits inside it, different from Democritus's vision, but still recognizably a solid thing that filled its own volume with substance. Then, in 1911, everything changed again. A New Zealand physicist named Ernest Rutherford conducted one of the most famous experiments in the history of science. He and his colleagues Hans Geiger and Ernest Marsden fired tiny positively charged particles, called alpha particles, at an extremely thin sheet of gold foil. The gold foil was thin enough that it was only a few thousand atoms thick. If Thomson's plum pudding model was right, and atoms were uniformly solid spheres of charge, the alpha particles should have passed through with only slight deflections, like shooting bullets through a cloud of cotton candy. The positive charge spread through the atom would nudge them a little, but nothing dramatic. Most of them did pass straight through, but some of them didn't. Some alpha particles bounced back at extreme angles. A few even came almost straight back towards the source. Rutherford later said it was as if you fired a 15-inch artillery shell at tissue paper and it came back and hit you. This result was impossible if the atom was a uniform sphere of charge. Something inside the atom was incredibly dense and incredibly small. Dense enough to deflect those fast-moving alpha particles. Small enough that most particles missed it entirely and passed through the rest of the atom without hitting anything at all. Rutherford's conclusion was stunning. Almost all the mass of an atom is concentrated in a tiny nucleus at the center. This nucleus is incredibly small, roughly 100,000th the diameter of the atom itself. The electrons exist around this nucleus at relatively enormous distances, and between the nucleus and the electrons, there is nothing. Empty space. Pure, absolute nothingness. The atom is not a solid ball. It is not mostly solid with some gaps. It is overwhelmingly, staggeringly empty. More than 99.99999999999% of an atom's volume is empty space. The solid matter you thought filled the world barely exists at all. Let me help you understand just how empty. If you could blow up a hydrogen atom to the size of a football stadium, a massive structure hundreds of feet across, the nucleus would be about the size of a marble sitting at the center of the field. A single proton sitting alone at the 50-yard line. The electron would be a tiny speck somewhere up in the upper decks. And everything in between, the entire volume of the stadium, all that space from the field to the upper seats, would be empty. Not mostly empty, not nearly empty, completely empty. There would be nothing there at all. This means that the solid table you knock on is almost entirely empty space. The chair you're sitting on is almost entirely empty space. Your own body, every cell, every bone, every organ is almost entirely empty space. If you could somehow remove all the empty space from every atom in your body and compress the remaining matter together, nucleus to nucleus, your entire body would fit into a space far smaller than a grain of sand. Actually, all 8 billion people currently alive on Earth, compressed in this way, would fit into a volume roughly the size of a sugar cube. That's how empty atoms are. That's how empty you are. So why does the table feel solid? Why does the floor hold you up? If everything is overwhelmingly empty space, why don't you just fall through the chair? Why doesn't your hand pass through the coffee mug? The answer is electromagnetism. When your hand approaches the table, the electrons in your hand and the electrons in the table's surface repel each other. Electrons carry negative charge and like charges repel. This electromagnetic repulsion creates a force that your brain interprets as solidity. You're not actually touching the table in any physical sense. The atoms in your hand never come into contact with the atoms in the table. There's always a gap maintained by electromagnetic repulsion between their electron clouds. What you feel as solidity, as hardness, as the resistance of one object against another is actually the electromagnetic force pushing back against you. There's also a quantum mechanical effect called the Pauli exclusion principle at work here. Electrons resist being squeezed into the same quantum state, which contributes to the rigidity of matter and prevents atoms from collapsing through one another. But the key point remains. What feels like solid contact is really a force interaction across a gap. There is no physical contact. There never has been. Everything you have ever touched in your entire life, you haven't really touched. Every handshake, every hug, every time you've picked up a glass of water or felt rain on your skin, it was electromagnetic forces interacting across a tiny gap, not matter contacting matter. The sensation of touch is an electrical interaction between the electron clouds of different atoms. Atoms never truly touch each other. They push each other away through their electromagnetic fields. The feeling of solidity is an electromagnetic illusion. Useful, reliable, consistent, but still fundamentally an illusion. This was already a radical departure from how people imagined the physical world. The atom had gone from being an indestructible, solid ball to being a mostly empty structure held together by invisible forces. In just 2 decades, the picture of matter had transformed from something simple and intuitive into something deeply counterintuitive. But at least there were still particles. There were still things in there, even if those things were tiny and surrounded by emptiness. The electron was still an electron. The nucleus was still a nucleus. They were small, but they were real physical objects with definite positions and properties. You could still imagine them as little spheres, just very small ones in a lot of empty space. That comfort was about to be completely destroyed. Because the next revolution in physics didn't just change what we knew about particles, it changed what a particle even is. And the implications are still shaking the foundations of our understanding of reality today. In 1913, a Danish physicist named Niels Bohr proposed a new model of the atom building on Rutherford's discovery. In Bohr's model, electrons orbited the nucleus like planets orbiting a star. Each electron followed a specific circular path at a specific distance from the nucleus. These orbits weren't arbitrary. Electrons could only occupy certain fixed orbits, certain allowed energy levels, and they could jump between these orbits by absorbing or emitting specific amounts of energy. When an electron absorbed a photon with exactly the right energy, it jumped to a higher orbit. When it dropped back down, it released a photon carrying that same specific energy. This explained why atoms emit light at specific frequencies rather than a continuous rainbow of colors. Each element produces its own unique pattern of spectral lines, like a fingerprint. Hydrogen emits red, blue-green, blue, and violet lines at very specific wavelengths. Sodium emits bright yellow. Neon emits the familiar reddish-orange glow of neon signs. Bohr's model explained these patterns beautifully and matched experimental data with impressive precision. But there was a problem with this picture. A deep, fundamental problem that would take another decade to fully reveal itself. In Bohr's model, electrons were still little particles, tiny charged balls following definite paths around the nucleus. They were small and they behaved strangely, jumping between orbits without crossing the space in between. But they were still fundamentally things. Objects with definite positions moving along definite trajectories at every moment. You could in principle point to an electron and say it's right there, moving in that direction at that speed. In the 1920s, this picture collapsed completely. The first crack came from experiments with light. In some experiments, light behaved exactly like a wave. It produced interference patterns, alternating dark and bright bands that formed when 2 waves overlapped. You could see this clearly in the double-slit experiment, first performed by Thomas Young back in 1801. When light was shone through 2 narrow slits onto a screen behind them, it didn't create 2 bright strips as you would expect from a stream of particles. Instead, it created an interference pattern. A series of alternating bright and dark bands spread across the screen. This was the unmistakable signature of wave behavior. When the crest of one wave meets the crest of another, they reinforce each other and you get a bright band. When the crest of one meets the trough of another, they cancel out and you get a dark band. Only waves do this. Particles simply don't produce interference patterns. A stream of particles would just make two bright strips behind each slit. But in other experiments, light behaved exactly like a particle. When light hit a metal surface, it knocked electrons free from the metal. This is called the photoelectric effect. The strange thing was that the energy of the ejected electrons didn't depend on the brightness of the light. It depended on the light's frequency, which we perceive as color. Making the light brighter only knocked out more electrons. It didn't give any individual electron more energy. Albert Einstein explained this in 1905 by proposing that light comes in discrete packets of energy, which we now call photons. Each photon carries a specific amount of energy determined by its frequency. When a photon hits an electron in the metal, it transfers its energy to that electron. If the photon's energy is high enough, the electron escapes the metal surface. If it isn't, nothing happens. No amount of additional low-energy photons will do the job. You need one photon with the right amount of energy. It was one of the most counterintuitive results in the history of physics, and Einstein received the Nobel Prize for explaining it. This was baffling. Light was somehow both a wave and a particle at the same time. Not one or the other, but genuinely both, depending on how you measured it. It could spread out and interfere with itself like a wave, but it could also arrive at a detector as a discrete chunk of energy like a particle. This became known as wave-particle duality, and it was about to become even more unsettling. In 1924, a French physicist named Louis de Broglie made a stunning proposal in his doctoral thesis. He suggested that wave-particle duality wasn't just a property of light, it was a property of everything. Electrons, protons, neutrons, atoms, molecules. All matter, de Broglie argued, has wave-like properties. The wavelength associated with any particle depends on its momentum. Heavier, faster particles have shorter wavelengths. Lighter, slower particles have longer wavelengths. For everyday objects like baseballs and people, the wavelength is so incredibly tiny, trillions upon trillions of times smaller than an atom, that it's completely undetectable and has no practical effect. But for something as small and light as an electron, the wavelength is significant. It's comparable to the size of an atom itself. And at that scale, the wave nature can't be ignored. De Broglie's prediction was confirmed experimentally in 1927 by Clinton Davison and Lester Germer at Bell Labs in the United States. They fired a beam of electrons at a crystal of nickel and observed a diffraction pattern on the other side. The electrons were scattering off the regularly spaced atoms in the crystal lattice and producing interference, exactly the way waves diffract through a grating. In the same year, George Paget Thomson in England independently confirmed the result using a different method. Electrons, which everyone had assumed were tiny solid particles, were behaving like waves. De Broglie won the Nobel Prize. So did Davison and Thomson. Then came the most disturbing version of this experiment. The double-slit experiment performed not with light, but with single electrons. Physicists sent electrons one at a time through two narrow slits. One electron at a time. A single electron left the source, traveled toward the barrier with two slits, and arrived at a detector screen on the other side. Each electron arrived at the detector as a single point, a tiny dot at a specific location on the screen. That seemed particle-like. But after many thousands of electrons had been sent through, one by one, the dots on the screen built up into a pattern. And that pattern was an interference pattern. The same pattern produced by waves passing through two openings. Think carefully about what this means. Each electron went through the slits completely alone. There was no other electron anywhere nearby to interfere with. The experiment was designed so that only one electron existed in the apparatus at any given time. Yet the accumulated pattern showed interference. It was as if each individual electron somehow traveled through both slits simultaneously, interfered with itself along the way, and then arrived at the detector as a single localized dot. One electron, two paths, both taken at the same time. This defies everything our intuition tells us about how objects should behave. A ball thrown at a wall with two holes goes through one hole or the other. It doesn't go through both, but an electron does, or at least it behaves as though it does. When physicists tried to determine which slit the electron actually went through by placing a detector at one of the slits, the interference pattern vanished. The electrons suddenly behaved like ordinary particles, going through one slit or the other, producing two simple bands on the screen. But the moment you stopped observing which slit they passed through, the interference pattern returned. The very act of observation changed how the electron behaved. This experiment has been called the most beautiful experiment in physics. It has also been called the most disturbing, because it tells us something profound and deeply uncomfortable about the nature of reality at the smallest scales. Electrons are not tiny balls. They're not little solid objects following definite paths through space. Before they're detected, before they interact with a measuring device, they don't have a definite position at all. They exist as a spread out wave of probability, taking all possible paths simultaneously. Only when they interact with something, only when they're measured, do they appear at a single specific location. And this wasn't just true for electrons. Over the following decades, the same wave-like behavior was confirmed for neutrons, for whole atoms, and even for surprisingly large molecules. In 2019, physicists at the University of Vienna demonstrated wave-like interference with molecules consisting of up to 2,000 atoms. Molecules with a combined mass of more than 25,000 atomic mass units. These were large, complex organic molecules, and they still displayed unmistakable interference patterns. At a fundamental level, nothing in the universe behaves like a solid little object. Everything has this underlying wave nature. Everything is, at bottom, something more like a ripple than a thing. Werner Heisenberg formalized part of this strangeness in 1927 with his famous uncertainty principle. This principle states that you cannot simultaneously know both the exact position and the exact momentum of any particle with perfect precision. The more accurately you determine where a particle is, the less accurately you can know how fast it's moving, and vice versa. This is not a limitation of our instruments. It's not that our technology is too crude or that we accidentally disturb the particle by measuring it. It's a fundamental feature of nature. The particle genuinely does not possess both a definite position and a definite momentum at the same time. These properties are not just unknown to us. They are physically undefined until a measurement is performed. Think of it this way. Imagine trying to pinpoint where an ocean wave is. You can point to the crest, but the wave isn't just the crest. It extends in both directions, spread out across the water. A wave that's spread out over a long distance has a very well-defined wavelength and frequency. But the more localized a wave becomes, the harder it is to define its wavelength. Position and wavelength are complementary descriptions. You can have one sharply defined or the other, but not both simultaneously. Heisenberg showed that the same trade-off applies to every particle in the universe, because particles are, at their core, wave-like phenomena. By the late 1920s, the old picture of the atom had been completely demolished. Rutherford's miniature solar system, with electrons orbiting the nucleus in neat circular paths, was gone. In its place was something far more unsettling. Electrons didn't orbit the nucleus in paths at all. They existed as probability clouds, fuzzy, spread-out distributions of likelihood surrounding the nucleus in three-dimensional shapes called orbitals. If you measured an electron's position, you'd find it somewhere. But you couldn't predict exactly where in advance. You could only calculate the probability of finding it in any given region of space. The electron wasn't in one place. It was smeared across all possible locations simultaneously, weighted by probability until a measurement forced it to appear at a specific point. This is quantum mechanics, the most successful and precisely tested theory in the history of science. Its predictions have been confirmed with astonishing accuracy across countless experiments. Every piece of modern technology you use, from the smartphone in your pocket to the computer chips in your car, relies on quantum mechanics being exactly correct. And what quantum mechanics tells us is something that shakes the very foundations of how we understand reality. The particles that make up your body, the electrons in every atom, the quarks inside your protons and neutrons, the photons that carry light to your eyes, none of them are tiny, solid objects. They don't have definite positions or definite paths until they interact with something. They behave like waves. They can exist in multiple states at once. They interfere with themselves. They are fundamentally, irreducibly, not things in the way we normally understand that word. The image of solid particles rattling around inside atoms is as outdated as the flat Earth. So if particles aren't really particles in the traditional sense, what are they actually? What is this wave-like essence that constitutes everything in the universe? If you pull away the image of tiny balls orbiting nuclei, if you completely let go of the picture of matter as solid little objects bouncing around in otherwise empty space, what on earth replaces it? The answer to this question took decades of painstaking work by some of the most brilliant physicists who ever lived. People like Paul Dirac, who first combined quantum mechanics with Einstein's special relativity. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who independently developed the full mathematical framework, and many others who tested, refined, and confirmed their ideas through experiment after experiment. The answer they arrived at is stunning in both its elegance and its strangeness. Particles are not fundamental. They are not the deepest layer of reality. Something else is. The particles we observe, every electron, every photon, every quark, they are excitations, ripples, vibrations, not vibrations, in some mysterious, invisible substance, but vibrations in something even more fundamental than the particles themselves. They are vibrations in fields that stretch across every point in space, fields that have been there since the beginning of the universe and will remain until its end. Fields that exist everywhere, at every location, whether or not any particle is present, whether or not anyone is looking, whether or not anything at all is happening. The universe is not made of particles floating in empty space. The universe is made of fields, and particles are just what happens when those fields get disturbed. This is not a metaphor. This is not a simplification for popular audiences. This is not an analogy or a teaching tool or a way of making something complicated sound poetic. This is the actual, literal, current best understanding of reality according to our deepest confirmed theory of nature. The particles you learnt about in school, the electrons and protons and neutrons, they are not the real story. They're just the part of the story we noticed first because they're the part that shows up when you build detectors and smash things together. The real story is the fields, and that story is about to take us somewhere truly extraordinary. So what exactly is a field? This word gets thrown around a lot in physics, but most people have never been told what it actually means. And the reason is that physicists tend to describe fields using mathematics, using equations and symbols that most people never encounter. But the concept itself is not complicated. In fact, you already have an intuitive sense of what a field is. You just might not realize it yet. Let's start with something you've experienced your entire life: gravity. Right now, sitting wherever you are, you feel the pull of the earth beneath you. You feel your weight pressing down into your chair. If you pick up a book and let go, it falls. Every time, without fail, it falls toward the earth. You've known this since you were an infant. Gravity is perhaps the most familiar force in your life. But here's the question that troubled physicists for centuries. How does the earth pull on the book? The earth is down there, beneath your feet. The book is up here, in your hand. There's a gap between them. Air, empty space, whatever you want to call it. The earth and the book are not touching. They're not connected by a rope or a chain or any visible mechanism. And yet, the moment you let go, the book accelerates toward the earth, as if something is pulling it. Something invisible. Something that reaches across the gap between the book and the ground and exerts a force. Isaac Newton was the first person to describe gravity mathematically. In 1687, he published his law of universal gravitation. Every object with mass attracts every other object with mass. The strength of that attraction depends on the masses involved and the distance between them. Newton's equations were brilliant. They could predict the motion of planets around the sun, the trajectory of cannonballs, the behavior of tides. They worked with extraordinary precision. But Newton himself was deeply troubled by something his equations couldn't explain. How does gravity actually work? How does the sun, 93 million miles from Earth, exert a gravitational pull on our planet? What is the mechanism? His equations described what gravity does, but they said nothing about how gravity reaches across empty space. This bothered Newton enormously. In a letter to a colleague, he wrote that the idea of one body acting on another through a vacuum without any intermediary was so absurd that no one with any competent faculty of thinking could ever accept it. Newton knew his theory was incomplete. He had described gravity's behavior perfectly, but he had no idea what gravity actually was. For about 150 years, most physicists just accepted this mystery and moved on. The equations worked, but the question lingered. How do forces act across empty space? The answer came from an unlikely source, not from someone studying gravity, but from someone studying magnets. In the 1830s, a self-taught English scientist named Michael Faraday was conducting experiments with electricity and magnetism. Faraday had almost no formal education. He had never attended university. He couldn't do advanced mathematics, but he had an extraordinary physical intuition. an ability to visualize and imagine the invisible forces he was studying in ways that university-trained scientists simply couldn't. Faraday performed an experiment that you might have done in school. He placed a bar magnet on a table and sprinkled iron filings around it. The iron filings arranged themselves into a pattern. They formed curved lines emanating from one pole of the magnet, sweeping through space and curving back to the other pole. Beautiful, graceful arcs of iron dust, tracing invisible pathways through the air around the magnet. You could see the pattern clearly. It wasn't random. It had structure. It had shape. The iron filings were revealing something that was there all along. Something invisible that existed in the space surrounding the magnet. Faraday looked at these patterns and had a profound insight. He proposed that the magnet wasn't simply exerting a force on distant objects through some mysterious action at a distance. Instead, the magnet was creating something in the space around it. Something real, something physical, something that existed at every point in the surrounding space, whether or not there was anything there to feel it. Faraday called these invisible structures lines of force, and the space filled with these lines of force, that was what he called a field. This was a revolutionary idea. Before Faraday, physicists thought of forces the way Newton had. Two objects interact directly, somehow reaching across empty space to push or pull on each other. Faraday proposed something completely different. The magnet doesn't reach across space to pull on the iron filings. Instead, the magnet creates a field that fills the space around it. The field exists everywhere around the magnet, extending outward in all directions. And when the iron filings are placed in this field, they feel its influence at their own location. The interaction is local. The filings respond to the field right where they are, not to the distant magnet directly. Think about what this means. In Faraday's picture, the space around the magnet is not empty. It looks empty. You can't see anything there with your eyes, but the field is there. It fills the space. It has strength and direction at every point. If you move a compass through the space around a magnet, the needle swings and points in different directions at different locations. This isn't because the magnet is reaching out and turning the needle from a distance. It's because the needle is responding to the field at its current location. The field is right there, surrounding the needle, and the needle aligns with it. This subtle shift in thinking from action at a distance to a field-filling space is one of the most important conceptual revolutions in the history of science. It changed what we mean by empty space. Before Faraday, empty space was just that. Empty. A void. A gap between objects where nothing existed. After Faraday, empty space became something. It became the medium through which forces act. It became a place where fields exist, invisible but real, carrying energy and exerting influence. Faraday applied the same idea to electricity. He showed that electric charges create electric fields in the space around them, just as magnets create magnetic fields. A charge doesn't reach across space to push or pull on another charge. Instead, the first charge creates a field. The second charge feels that field at its own location and responds accordingly. The field is the intermediary that Newton was looking for but never found. Faraday also made a crucial experimental discovery. He showed that changing a magnetic field creates an electric field, and changing an electric field creates a magnetic field. Electricity and magnetism weren't separate phenomena. They were deeply intertwined. A moving magnet could generate an electric current in a nearby wire because the changing magnetic field was creating an electric field that drove the electrons. This discovery, electromagnetic induction, is the basis of nearly all electrical power generation today. Every power plant, every generator, every transformer, every electric motor relies on Faraday's discovery that fields interact with each other in space. But Faraday couldn't express his ideas thematically. He thought in pictures, in physical images of lines of force and fields filling space. Many of the formerly trained physicists of his day dismissed his ideas as vague and unscientific because they lacked mathematical rigor. They preferred the clean, precise equations of Newton-style action at a distance. Faraday's fields, to them, seemed like hand-waving. Imaginative, perhaps, but not real physics. Then along came James Clerk Maxwell, a Scottish physicist who was as gifted mathematically as Faraday was intuitively. Maxwell took Faraday's visual, physical ideas about fields and translated them into a set of precise mathematical equations. These equations, published in their complete form in 1865, are known as Maxwell's equations. And they are among the most important equations in all of physics. Maxwell's equations describe how electric and magnetic fields behave, how they're created by charges and currents, how they change over time, how they interact with each other. But when Maxwell analyzed his own equations carefully, he found something nobody expected, something breathtaking. His equations predicted that a changing electric field would create a changing magnetic field, which would create another changing electric field, and so on. This chain reaction would propagate outward through space as a wave, a self-sustaining ripple in the electromagnetic field that would travel on its own, requiring no medium, no wire, no material to carry it. Just the field itself, oscillating back and forth, racing through space. Maxwell calculated the speed at which this wave would travel, and when he plugged in the known values for the strength of the electric and magnetic interactions, the answer he got was approximately 300,000 kilometers per second. Maxwell immediately recognized this number. It was the measured speed of light. The implication was stunning. Light is not a separate phenomenon from electricity and magnetism. Light is a wave in the electromagnetic field, a ripple, an oscillation. When you see a candle flame or a sunset or the glow of a distant star, what you are actually seeing is a wave in the electromagnetic field, a pattern of oscillating electric and magnetic disturbances that has traveled from the source to your eye. When you feel the warmth of sunlight on your face, you're feeling energy carried by oscillations in the electromagnetic field that left the sun 8 minutes ago and crossed 93 million miles of space. This was one of the greatest unifications in the history of science. Electricity, magnetism, and light, three phenomena that seemed completely unrelated, turned out to be three aspects of a single underlying reality: the electromagnetic field. One field filling all of space, and different kinds of disturbances in that field manifest as different phenomena. Static charges create steady electric fields, magnets create steady magnetic fields, and oscillating disturbances in the combined electromagnetic field travel through space as light, radio waves, X-rays, microwaves, gamma rays, and every other form of electromagnetic radiation. Maxwell's prediction was confirmed experimentally in 1888 by Heinrich Hertz. Hertz built an apparatus that created oscillating electric sparks, which produced electromagnetic waves. He then detected those waves across the room with a separate receiver. The waves traveled at the speed of light, exactly as Maxwell had predicted. Hertz had generated and detected radio waves for the first time. This discovery led directly to the development of radio communication, television, radar, wireless networks, and every other technology that uses electromagnetic waves. All of it flows from the realization that fields are real, that they fill space, and the disturbances in those fields can travel as waves. So by the end of the 19th century, physicists had established something remarkable. At least one kind of field, the electromagnetic field, was undeniably real. It wasn't an abstraction or a mathematical convenience. It carried energy. It exerted forces. Waves could travel through it. Light was made of it. The space that looked empty to your eyes was actually filled with the electromagnetic field, which could be disturbed, excited, and set into oscillation. Now, this is where the story takes a dramatic leap forward into the 20th century and beyond, because the electromagnetic field was just the beginning. When physicists developed quantum mechanics in the 1920s, they realized that the wave-like behavior of particles and the field concept were pointing in the same direction. If light, which had been understood as a wave in the electromagnetic field, also behaved as particles called photons, then maybe the reverse was true as well. Maybe particles that we thought of as matter, like electrons, were actually waves in their own kind of field. An electron field that fills all of space, just as the electromagnetic field does. This idea was developed into a full theoretical framework over the course of the 1930s and 1940s. The result was quantum field theory. And this is where our understanding of reality fundamentally transforms. In quantum field theory, every type of fundamental particle in the universe corresponds to its own field. The electron has a field. The electron field. It exists everywhere, at every point in the universe, at all times. It's there in this room right now. It's there in the space between Earth and the Moon. It's there in the void between galaxies. It permeates everything. Every cubic centimeter of space, no matter how empty it might appear, contains the electron field. And the electron field is not the only one. Every type of fundamental particle has its own field. There's a field for each of the 6 types of quarks. The up quark field, the down quark field, the charm quark field, the strange quark field, the top quark field, and the bottom quark field. These quark fields are everywhere, filling all of space, just like the electron field. There's a muon field for muons, which are heavier cousins of the electron. There's a tau field for tau particles, which are even heavier. There are neutrino fields, 3 of them, 1 for each type of neutrino. Electron neutrinos, muon neutrinos, and tau neutrinos. All 3 neutrino fields permeate all of space. Then there are the fields associated with forces. The electromagnetic field we already discussed, which gives rise to photons. The strong nuclear field carried by particles called gluons, which holds quarks together inside protons and neutrons. This field is extraordinarily powerful at short ranges, which is why it's so hard to break apart an atomic nucleus. And there's the weak nuclear field, carried by particles called the W and Z bosons, which is responsible for certain types of radioactive decay. The weak field is what allows a neutron to transform into a proton, releasing an electron and a neutrino in the process. This is the mechanism behind beta decay, one of the most common forms of radioactivity. And then there's the Higgs field, but we'll get to that later. In total, the standard model of particle physics, our best current description of the fundamental building blocks of the universe, describes about 24 fundamental fields. These fields are not separate from the universe. They are the universe. They don't exist in space. They are what space is made of. They don't fill the void. They are the void. Every point in the universe, no matter how remote, no matter how empty it might seem, is the location of all these overlapping, coexisting fields simultaneously. Imagine it like this. Think of the ocean. The surface can carry waves of different sizes, speeds, and directions. Those waves can overlap, pass through each other, and interfere. Now imagine that instead of one ocean surface, there are 24 different surfaces, all occupying the same space simultaneously. Each surface can carry its own waves independently of the others. A wave on one surface doesn't necessarily create a wave on another. Each surface has its own properties and rules about what kinds of waves it can support. That's roughly what the universe is like. 24 or so quantum fields, all filling the same space, all overlapping, all capable of carrying their own excitations. And what we call particles are waves on these surfaces. An electron is a wave on the electron field. A photon is a wave on the electromagnetic field. A quark is a wave on the quark field. The particles aren't separate from the fields. They are the fields, or rather, they are what the fields do when they're disturbed. This is fundamentally different from how most people imagine reality. Most people think of particles as tiny objects that exist at specific locations in space, like tiny grains of sand scattered through an empty room. The fields, if they think about them at all, are secondary, just forces or influences that affect the particles. But in quantum field theory, it's exactly the other way around. The fields are primary. The fields are what actually exist. They are the fundamental entities, and particles are secondary. They are just patterns, excitations, temporary disturbances in the fields. The fields are the ocean, the particles are the waves. Let me make this concrete. Consider the electromagnetic field. It fills all of space. In most places, it's calm, not doing much, sitting in its lowest energy state. But when you flip a light switch and electricity flows through the filament of a light bulb, the accelerating electrons in the filament disturb the electromagnetic field. They create ripples in it. Those ripples propagate outward at the speed of light, spreading through the room. When those ripples reach your eye, they interact with the electron field in the atoms of your retina, transferring energy and creating signals that your brain interprets as light. What you experienced as turning on a light was actually disturbing one field, creating waves in that field, and those waves traveling through space to disturb another field in your eye. Or consider the electron field. It's everywhere. In this room, in outer space, everywhere. Most of the time, in most places, it's in its ground state, its lowest energy configuration. It's calm. But inside every atom around you, the electron field is excited. There are localized vibrations in the electron field, concentrated around atomic nuclei. These vibrations are what we call electrons. They're not tiny balls orbiting the nucleus. They're localized patterns of excitation in the electron field. The field is vibrating at those locations, and the vibrations are stable. They persist. And we give those persistent, localized vibrations a name. We call them electrons. When an electron moves from one atom to another, what actually happens is that the excitation in the electron field shifts from one location to another. The electron field decreases its excitation at one point and increases it at another. Nothing literally travels from point A to point B in the way a baseball travels through the air. Instead, a pattern in the field shifts position. It's more like a wave moving across water. The water itself doesn't travel horizontally. It moves up and down in place. But the pattern, the wave, the disturbance that travels, the electron is the disturbance. Not a thing that has the disturbance, but the disturbance itself. This is a genuinely difficult concept to absorb because our brains are wired to think in terms of objects. Things that you can pick up, move around, count, and track. We think of the world as made of stuff. Particles are the ultimate stuff. The building blocks. The Lego bricks of reality. But quantum field theory says that's wrong. There is no stuff. There are only fields. And what we perceive as stuff, the particles, the matter, the tangible things of the world, are really just patterns, vibrations, excitations, temporary configurations of the fields that happen to be stable enough to persist. Here's another way to think about it. Imagine a perfectly still lake on a windless morning. The surface is flat and smooth. There's nothing to see. Now, imagine something disturbs the lake. Maybe a rock falls in or a fish jumps. Ripples spread across the surface. Those ripples are real. They carry energy. They can move things. They interact with the shore. But what are they? Are they things in the way a rock or a fish is a thing? Not really. They're disturbances in the lake's surface. The surface is what's real. The ripples are what the surface does when it's disturbed. Take away the lake, and the ripples can't exist. But the lake can exist perfectly well without any ripples. Quantum fields are like the lake. They're what's truly there. Particles are like the ripples. They're what the fields do when something happens. The fields are fundamental. The particles are derived. The fields can exist without particles, and they do. In vast stretches of empty space, the fields are there in their ground state, calm, undisturbed. No particles are present, but the fields are. They're always there. Now, here's something crucial that separates a quantum field from a classical field like the ones Faraday and Maxwell described. In classical physics, a field can be perfectly calm. You can have an electromagnetic field with zero disturbance, zero energy, completely still and quiet. But in quantum mechanics, that's not possible. The uncertainty principle that Heisenberg discovered doesn't just apply to particles, it applies to fields as well. A quantum field can never be perfectly still. Even in its ground state, even in its lowest possible energy configuration, the field fluctuates. It jitters. It vibrates randomly at every point in space, constantly, everywhere, all the time. These are called quantum fluctuations or vacuum fluctuations. They're tiny, incredibly small, but they're real. They have measurable consequences. The field is never exactly zero. It hovers around zero, fluctuating slightly up and down like a guitar string that hums faintly even when no one is playing it. You might think the string is silent, but hold your ear close enough and you'll hear a whisper of vibration. It's never truly still. Neither are quantum fields. They can't be still. The laws of quantum mechanics forbid it. There is always some residual activity, some minimum level of vibration that can never be removed, no matter how cold you make the system or how thoroughly you isolate it from outside disturbances. This means that what we call empty space, the vacuum, the void, is not empty, not even close. Every point in the vacuum of space contains all the quantum fields of the universe, and every single one of those fields is fluctuating. The vacuum is a seething, dynamic, active place. It just looks empty because the fluctuations are happening at scales too small, and too fast for us to directly perceive. But we can detect these fluctuations indirectly. They have real physical effects that have been measured in laboratories with extraordinary precision. And those effects confirm that the fields are really there, that the vacuum is really active, and that what we call empty space is far from empty. The evidence for this is so compelling, so precisely measured, and so well confirmed by multiple independent experiments that there is no serious doubt among physicists that quantum fields and their vacuum fluctuations are real. This point is important enough to emphasize. Fields are not mathematical abstractions. They're not convenient fictions that physicists use to make calculations easier. They're not metaphors or models that approximate some deeper reality. As far as the most precisely tested theory in science can tell us, fields are the deepest reality we've found. They are what exists. Everything else, particles, forces, matter, light, is a consequence of what the fields do. The theory that describes all of this, quantum field theory, is the foundation of the standard model of particle physics. The standard model is not speculative. It is the most thoroughly tested and precisely confirmed theory in the history of science. The magnetic moment of the electron, for example, has been measured experimentally and calculated using quantum field theory, and the two values agree to better than 1 part in 10 billion. That's like predicting the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. No theory in any field of science has ever achieved this level of agreement between prediction and measurement. And the standard model is built entirely on the concept of fields. When physicists at CERN accelerate particles to nearly the speed of light and smash them together, the new particles that emerge from the collisions are explained by interactions between quantum fields. When a particle is created in a collider, energy is being pumped into a field, exciting it enough to create a new vibration. When a particle decays, one vibration in a field transforms into vibrations in other fields, following precise rules that quantum field theory predicts. This framework has explained every experiment in particle physics for over 50 years. Every known particle, from the familiar electron to the exotic top quark, is an excitation of its corresponding field. Every known force, from electromagnetism to the strong and weak nuclear forces, is mediated by the exchange of field excitations. The entire particle zoo, that bewildering collection of quarks and leptons and bosons that you might have seen arranged in a neat chart, is really a catalogue of fields. Each entry in the chart represents a field that fills all of space, and the particle listed is what happens when that field gets excited. So the next time someone asks you what the universe is made of, the honest answer, according to our best understanding of physics, is not atoms. It's not particles. It's not matter and energy. The universe is made of fields, about 24 quantum fields that permeate every point in space and time, overlapping, interacting, fluctuating, vibrating. Everything you see and touch and feel is a pattern in these fields. Every star, every planet, every living thing, every grain of sand, every photon of light, all of it is field excitations. The empty space between the stars is not empty. It contains all of these fields in their ground state, fluctuating quietly. The air in this room is not just a collection of molecules bouncing around. Each of those molecules is a complex pattern of excitations in quark fields, electron fields, and gluon fields, all interacting through the electromagnetic field and the strong nuclear field. Your body is a staggeringly intricate arrangement of field excitations roughly 7 billion atoms, each one a stable configuration of vibrations in the underlying quantum fields, all interacting, all sustained by the same entities that fill the entire universe. Fields are everywhere. They've been everywhere since the earliest moments of the universe's existence. They will be everywhere for as long as the universe endures. And they are not just part of reality. As far as physics can determine, they are reality. Everything else is what the fields do. But if the vacuum is truly filled with fluctuating fields, if even the emptiest space in the universe is humming with this invisible quantum activity, then surely there should be some way to detect it directly. Some physical consequence that we can point to and say, that effect is caused by the fields in the vacuum. That proves they're real, not just theoretical constructs. And there is, in fact, there are several. The evidence is not ambiguous or indirect. It's precise, repeatable, and stunning. And it's going to show us that the vacuum, that thing we thought was nothing, is one of the strangest and most active places in the entire universe. Now, let's go deeper. Because if fields are really the fundamental stuff of the universe, and particles are just excitations in those fields, then we need to confront something uncomfortable. Everything you were taught about particles is, at best, a convenient simplification. At worst, it's misleading. The picture you have in your head, tiny little balls bouncing around inside atoms, little spheres zipping through space, that picture is wrong. Not approximately wrong, not close, but not quite. Fundamentally, deeply, structurally wrong. And replacing it with the correct picture changes everything about how you understand matter, energy, forces, and even what it means for something to exist. Let's start by really nailing down what it means to say a particle is an excitation in a field, because this is the single most important idea in modern physics, and most people have never heard it explained clearly. Think about a guitar string. When the string is at rest, it's just sitting there, stretched taut between two fixed points, not vibrating, not making any sound. It's in its lowest energy state, its ground state. Now pluck it. The string vibrates. It oscillates back and forth at a specific frequency determined by its length, its tension, and its thickness, producing a musical note. That vibration is not a separate object sitting on the string. It's not a thing that was added to the string from the outside. It's what the string itself is doing. The vibration is a behavior of the string, a pattern of motion, an excitation of something that was already there. If you pluck the string harder, the vibration is larger, more energetic, louder. If you pluck it gently, the vibration is smaller, softer. But in both cases, the vibration is not a separate entity from the string. It is the string doing something. Now extend this idea to the entire universe. Replace the guitar string with a quantum field, one that fills all of space in every direction. When that field is in its ground state, it's calm. No particles are present. But when energy is added to the field at some location, the field vibrates there. It gets excited. That localized excitation, that vibration in the field, is what we detect as a particle. An electron is not a tiny ball. It is a localized vibration in the electron field. The electron field extends through all of space. In most places, it's in its ground state. But in certain locations, around atomic nuclei for instance, the field is excited. Those excitations are stable. They persist. And when we build detectors and perform measurements, we detect those excitations as discrete, localized objects. We call them electrons. But the electron isn't separate from the field. It is the field. Or more precisely, it's something the field is doing at that location. A photon is not a tiny pellet of light. It is a vibration in the electromagnetic field. When you turn on a flashlight, the energy from the battery excites the electromagnetic field. Ripples propagate outward from the bulb at the speed of light. Those ripples are photons. They're not objects riding on top of the field like boats on an ocean. They are the ocean doing something. They are disturbances in the electromagnetic field itself, carrying energy from one place to another. A quark is not a tiny speck inside a proton. It is a vibration in the quark field. The quarks bound together inside a proton are 3 localized excitations in the quark field, held together by excitations in the gluon field, which is itself another quantum field filling all of space. The proton is not a bag containing 3 tiny balls. It's a complex dynamic pattern of interacting field excitations, multiple fields vibrating together in a stable configuration that persists for incredibly long periods. Protons are so stable, in fact, that their average lifetime exceeds 10 to the power of 34 years. That's far longer than the current age of the universe, which is only about 13.8 billion years. A proton is a vibration that essentially never stops. This way of thinking changes what it means for a particle to be created or destroyed. In the old particle picture, creating a particle meant making a new tiny object appear from nothing. That sounds almost magical. Where does it come from? How does a new thing pop into existence? But in the field picture, creating a particle is not mysterious at all. It's simply exciting a field. You add energy to a field at some location, and the field starts vibrating there. That vibration is the new particle. Nothing was created from nothing. A field that was already there, everywhere in its ground state, simply received enough energy to become excited at a particular point. Similarly, when a particle is destroyed, the field doesn't disappear. The excitation stops. The energy gets transferred to other fields. The original field returns to its ground state at that location. The field is still there. It's always there. Only the vibration has changed. This is what happens in particle colliders like the Large Hadron Collider at CERN. When protons are smashed together at nearly the speed of light, the enormous energy of their collision excites various quantum fields. New vibrations appear in fields that were previously in their ground state. We detect those vibrations as new particles emerging from the collision point. Electrons, muons, quarks, photons, W bosons, Z bosons, even Higgs bosons. These particles weren't hiding inside the original protons waiting to come out. They were created fresh by the collision energy exciting different fields. The energy went into the electron field and created electrons. It went into the muon field and created muons. It went into the Higgs field and created Higgs bosons. Each field responds to the available energy independently, producing its own characteristic excitations according to well-defined rules. This also explains one of the most puzzling features of the particle world. Why are all electrons identical? In the entire observable universe, spanning 93 billion light years, containing roughly 10 to the power of 80 electrons, every single one of those electrons has exactly the same mass, exactly the same charge, exactly the same spin, exactly the same magnetic moment. There are no fat electrons or thin electrons, no old electrons or young electrons, no slightly worn electrons or brand new electrons, no electrons that are slightly different from other electrons in any measurable way whatsoever. Every single electron in existence is perfectly, absolutely, flawlessly identical to every other electron in existence. If particles were tiny objects, like miniature billiard balls manufactured somewhere, this would be incredibly strange. Why would everyone be exactly the same? Even the most precisely machined components in a factory have tiny differences. Perfect uniformity across the entire universe demands an explanation. But if electrons are excitations in a single field, the electron field, then their perfect identity is obvious. Of course, they're all the same. They're all vibrations in the same field. Just as every wave on the ocean is made of the same water, every electron is made of the same field. The electron field has specific properties. Its excitations have a specific energy, a specific charge, a specific spin. Every excitation of the electron field has those same properties because the field itself determines them. Asking why all electrons are identical is like asking why all ripples on a pond are made of water. They're made of water because the pond is water. Electrons are identical because the electron field is one thing, and all electrons are excitations of that one thing. This also applies to every other particle. All photons are identical because they're all excitations of the same electromagnetic field. All up quarks are identical because they're all excitations of the same up quark field. The uniformity of particles across the universe, which seemed like a deep mystery in the old particle picture, is trivially explained in the field picture. There is only one electron field. It fills all of space. Every electron everywhere in the universe, in your body, in a star 10 billion light years away, is a vibration in this same single field. They're connected, in a sense, through the field that underlies them all. Now here is where things get truly strange, because the fields don't just sit there passively waiting to be excited. Even when no particles are present, even when a field is in its lowest energy state, it's not perfectly still. Quantum mechanics forbids it. Heisenberg's uncertainty principle, which we discussed earlier, applies to fields just as it applies to particles. A field cannot have both a precisely defined value and a precisely defined rate of change at the same time. This means the field is always fluctuating, always jittering. Even in the vacuum, even in the emptiest space imaginable, the fields are vibrating. These vacuum fluctuations are not just theoretical predictions. They have real, measurable, physical consequences. And those consequences have been confirmed by some of the most precise experiments ever performed. Let me tell you about the most dramatic ones. The first is called the Casimir effect. In 1948, a Dutch physicist named Hendrik Casimir made a remarkable prediction. He said that if you place two uncharged metal plates very close together in a perfect vacuum, the plates will be pushed toward each other by a measurable force, not by gravity, not by static electricity, not by any force that classical physics can explain. The force comes directly from the vacuum itself, from the quantum fluctuations of the electromagnetic field in the space between and around the plates. Here's why this happens. The electromagnetic field fluctuates everywhere, constantly. These fluctuations can be thought of as waves with every possible wavelength. Outside the plates, in the open space, all wavelengths of fluctuation are possible. The field can fluctuate at any frequency it likes. But between the plates, the situation is different. The plates impose a boundary condition. Only certain wavelengths can fit between them. Wavelengths that match the gap between the plates. Long wavelengths that don't fit are excluded. This means there are more possible fluctuations outside the plates than between them. More fluctuations mean more energy, and more energy means more pressure. The imbalance in fluctuation pressure between the outside and the inside pushes the plates together. This is extraordinary. Two metal plates in a perfect vacuum with nothing between them, no air, no radiation, no particles of any kind, are pushed together by the quantum activity of the electromagnetic field. The vacuum itself exerts a measurable physical force. Casimir predicted this effect in 1948, but it was extremely difficult to test because the force is incredibly small. For plates separated by about 1 micrometer, roughly 1/100th the width of a human hair, the Casimir force is equivalent to the weight of about 1/10,000th of a gram. That's far less than you could feel, and it's easily masked by other forces like static electricity or gravity. You need plates that are extraordinarily smooth, positioned extremely close together with nanometer precision, and you need to eliminate every other possible source of force. It wasn't until 1997 that Steve Lamoureux at the University of Washington performed a precise measurement using a gold-coated sphere near a flat plate, confirming Casimir's prediction to within 5%. Since then, the measurements have improved dramatically. Today, the Casimir effect has been measured with extraordinary accuracy using advanced microfabrication techniques, and it matches the predictions of quantum field theory precisely. The Casimir effect is not subtle or ambiguous. It is a direct, physical, measurable consequence of the fact that quantum fields fluctuate in the vacuum. It proves that the vacuum is not empty. The fields are there. They're active, and their activity has real physical effects that you can detect in a laboratory. The second piece of evidence is called the Lamb shift. In 1947, American physicist Willis Lamb and his student Robert Rutherford made an incredibly precise measurement of the energy levels of hydrogen atoms. According to the original equations of quantum mechanics, developed by Paul Dirac in the late 1920s, two specific energy levels in hydrogen should have exactly the same energy. They should be perfectly degenerate, as physicists say. But Lamb and Rutherford found that these levels were not exactly the same. There was a tiny difference. The levels were shifted relative to each other by a small but unmistakable amount. What caused this shift? The answer turned out to be vacuum fluctuations. The electron in a hydrogen atom is not moving through empty space. It's moving through a sea of fluctuating quantum fields. The electromagnetic field around the electron is constantly fluctuating, and these fluctuations jiggle the electron, giving it a tiny random kick in every direction at every moment. On average, these kicks cancel out and the electron stays approximately where quantum mechanics says it should be. But the kicks affect the electron's energy slightly, because the electron spends a tiny fraction more of its time at slightly different distances from the nucleus than it otherwise would. The fluctuations of the electromagnetic field around the electron cause its energy levels to shift by a small but measurable amount. This is the Lamb shift. The calculation of the Lamb shift using quantum field theory was one of the great triumphs of 20th century physics. It was performed independently by Hans Bethe, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, each using somewhat different mathematical approaches but arriving at the same answer. Their calculated value matched Lamb's experimental measurement with stunning precision. This agreement was so impressive that it essentially established quantum field theory as the correct framework for understanding the quantum world. Feynman, Schwinger, and Tominaga shared the Nobel Prize in 1965 for this work. The Lamb shift tells us something profound. Even inside an atom, the fields are fluctuating. The electron doesn't exist in a calm, quiet void. It exists in a churning sea of field activity, and that activity has measurable effects on how atoms behave. Every atom in your body is affected by vacuum fluctuations. The precise energy levels of your atoms, the frequencies of light they can absorb and emit, the chemical bonds they form, all of these are slightly modified by the restless activity of quantum fields in the vacuum. You are, quite literally, shaped by the quantum fluctuations of empty space. The third piece of evidence involves something called virtual particles. This is perhaps the strangest consequence of vacuum fluctuations, and it requires careful explanation because the concept is widely misunderstood. In quantum field theory, the fluctuations of the vacuum can be described in terms of particle-antiparticle pairs that briefly pop into existence and then annihilate each other, disappearing again almost instantly. These are called virtual particles. An electron and a positron, the electron's antimatter counterpart, can spontaneously appear from the fluctuating electron field, exist for an unimaginably brief moment, far less than a billionth of a second, and then collide and annihilate, returning their energy to the field. A quark and an antiquark can similarly flicker into existence from the quark field and vanish again. This happens constantly, everywhere, at every point in space, for every type of field simultaneously. Now, it's important to be careful here. Virtual particles are not exactly the same as real particles. You can't catch a virtual particle in a detector the way you can catch a real electron. Virtual particles don't have a definite mass in the way real particles do. They exist for such brief periods and in such uncertain states that they're better understood as a mathematical description of the field's fluctuations rather than as actual tiny objects popping in and out of existence. Physicists debate the exact ontological status of virtual particles, whether they are real entities or just useful bookkeeping devices in calculations. But what is not debated is that the underlying fluctuations they describe are real. The Casimir effect is real, the Lamb shift is real. The physical effects attributed to vacuum fluctuations are measured facts. There's another dramatic confirmation of vacuum fluctuations that's worth mentioning: Hawking radiation. In 1974, Stephen Hawking made a groundbreaking theoretical prediction about black holes, and he showed that the quantum fluctuations of fields near a black hole's event horizon should cause the black hole to slowly emit radiation and lose mass over time. The idea, put simply, is that virtual particle pairs forming near the event horizon can be separated by the black hole's gravity. One particle falls in, the other escapes. The escaping particle carries away energy, and the black hole loses a corresponding amount of mass. Over enormous timescales, this process would cause the black hole to slowly evaporate. Hawking radiation has not been directly observed because the effect is extraordinarily weak for any black hole we could currently detect. A black hole with the mass of our sun would have a temperature far colder than the cosmic microwave background, making its radiation unmeasurably faint. But the theoretical framework behind Hawking radiation is built on the same vacuum fluctuations that produce the Casimir effect and the Lamb shift. And analog experiments using sound waves in fluids have confirmed the basic mechanism. Most physicists believe Hawking radiation is real, even though we haven't yet observed it directly from an actual black hole. All of this leads to a remarkable conclusion. The vacuum, the emptiest possible space, is not empty. It never has been. It never can be. The vacuum is the ground state of all quantum fields simultaneously. Every field is present. Every field is fluctuating. The vacuum has energy. It has structure. It has measurable physical properties. It exerts forces. It shifts atomic energy levels. It shapes the behavior of every particle and every atom in the universe. When you look out at deep space, at the vast darkness between the stars, you're not looking at nothing. You're looking at every quantum field in the universe, all of them present, all of them in their ground state, all of them fluctuating with a minimum energy that can never be removed. That darkness between the stars is filled with the electron field, the quark fields, the gluon field, the electromagnetic field, the weak force fields, the neutrino fields, the Higgs field, all of them overlapping, all of them active. Space is a plenum, not a void. It is full, not empty. What we call the vacuum is the quietest the fields can be. But quiet is not silent. There's always activity, always fluctuation, always the hum of quantum fields doing what quantum fields do. This understanding of the vacuum has enormous consequences for physics. One of the most important is the cosmological constant problem, which is sometimes called the worst prediction in the history of physics. When physicists try to calculate the total energy of all the vacuum fluctuations in the universe, the number they get is absurdly large. By some estimates, the vacuum should contain roughly 10 to the power of 113 joules of energy per cubic meter. If this energy were real, if it gravitationally affected the universe the way normal energy does, it would curve space-time so dramatically that the universe would be crushed into a volume smaller than an atom. Obviously, this hasn't happened. The universe exists. It's large and relatively flat. Space-time is not crushed or violently curved. Stars shine. Galaxies rotate peacefully. So either the vacuum energy is much, much smaller than the calculation suggests, or something is cancelling most of it out with almost unbelievable precision. When astronomers measure the actual energy density of the vacuum by observing the accelerating expansion of the universe, they get a number that is about 120 orders of magnitude, smaller than the theoretical prediction. That's a factor of 10 to the power of 120. It's the largest discrepancy between theory and observation in the entire history of science. Nobody knows why. This is one of the deepest unsolved problems in all of physics. And some physicists consider it the single most important question in fundamental science today. The vacuum energy that does exist, the small amount that remains after whatever mysterious cancellation occurs, is what we call dark energy. It's the force driving the accelerating expansion of the universe. Every year, the space between distant galaxy clusters grows a little larger, and the expansion is speeding up, not slowing down as you might expect from gravity pulling everything together. Something is pushing the universe apart, and the best explanation we have is that the energy of the vacuum itself, the residual quantum energy of all those fluctuating fields, exerts a repulsive gravitational effect on cosmological scales. The quantum fluctuations of fields in empty space are literally pushing the universe apart. Think about that for a moment. The same vacuum fluctuations that push two metal plates together in the Casimir effect. The same fluctuations that shift energy levels in hydrogen atoms. Those same fluctuations on a cosmic scale are driving the expansion of the entire universe. The activity of quantum fields in the vacuum isn't just a curiosity or a footnote. It may be the dominant force shaping the large-scale fate of the cosmos. Let me also tell you about something called the Schwinger effect, because it illustrates just how much latent potential the vacuum contains. In 1951, Julian Schwinger calculated that if you apply a strong enough electric field to the vacuum, you can rip virtual particle pairs apart before they have a chance to annihilate. The electric field provides enough energy to turn virtual particles into real particles. Electron-positron pairs would spontaneously materialize from the vacuum. You would literally be creating matter from empty space. The electric field required to do this is enormous, roughly 1.3 times 10 to the power of 18 volts per meter. That's far beyond anything we can currently produce in a laboratory. For perspective, the strongest electric fields we can generate today using the most powerful lasers in the world are still roughly 1,000 times too weak. The original Schwinger effect has not yet been directly observed in its pure form. However, analog versions of the effect have been demonstrated in graphene experiments, where the mathematical structure of Schwinger pair production was successfully replicated in a condensed matter system, and the theoretical framework is well understood and universally accepted by physicists. The vacuum contains the potential for matter. Under the right conditions, with enough energy concentrated in a small enough region, particles can be pulled directly out of the vacuum, out of what appears to be nothing. But it isn't nothing. It's the ground state of quantum fields, and those fields contain the blueprint for every particle that could possibly exist. This brings us to a deep philosophical point about the nature of existence. In the field picture, a particle doesn't come from nowhere when it's created. It was always potentially there, latent in the field. The field existed before the particle. The field will exist after the particle is gone. The particle is temporary. The field is permanent. Particles come and go. They're created in collisions, in radioactive decays, in the hearts of stars. They're absorbed, they annihilate, they transform into other particles. But the fields never appear or disappear. They're always present. They're the enduring substrate of reality, and particles are the transient phenomena that play out on that substrate. What we call matter is really just a collection of especially stable field excitations. The quarks and electrons that make up your atoms are vibrations that happen to be extraordinarily long-lived. But they're still vibrations. They're still patterns in the fields. If the fields could somehow be removed, the particles wouldn't just lose their properties. They would cease to exist entirely. There would be nothing left. Not empty space, not a void, nothing. Because even empty space, even the void, is made of fields. This is the picture that emerges from almost a century of work in quantum field theory. The universe is not a container filled with objects. It's a collection of fields, everywhere, always, and the objects we see, the particles and atoms and molecules and stars and galaxies, are all patterns of activity in those fields. The solid world you experience every day, the table you knock on, the ground you walk on, the body you inhabit, all of it is field excitations. Vibrations in invisible, omnipresent quantum fields that stretch from here to the farthest reaches of the observable universe and beyond. The vacuum that appears empty is teeming with activity. Fields fluctuate. Virtual pairs flicker in and out. Energy fills what looks like nothing. And this hidden activity has consequences that range from the microscopic, shifting energy levels in individual atoms, to the cosmic, driving the accelerating expansion of the universe itself. You might wonder whether there's a limit to what we can extract from the vacuum, whether the energy locked in those fluctuating fields could somehow be harnessed. The short answer is that it's extraordinarily difficult and probably impossible with current or foreseeable technology. The energy of vacuum fluctuations is real, but it represents the lowest possible energy state of the fields. You can't easily extract energy from a system that's already in its ground state. It would be like trying to dig a hole at the bottom of the ocean. There's nowhere lower to go. The vacuum is the floor. You can't drain it further. But the fact remains that the vacuum is not nothing. It's the quieter state of something tremendously active. It's the ground floor of a building with an infinite number of stories above it. And the building itself, the structure that supports all those floors, is made of fields. Fields that exist everywhere. Fields that have always existed. Fields that make everything in the universe possible. There is one more field we haven't discussed yet. One that stands apart from all the others. One that does something no other field does. It gives particles their mass. Without it, every particle in the universe would be massless, moving at the speed of light, unable to form atoms, unable to form matter, unable to form you. This field is the Higgs field, and it changes everything one final time. Of all the fields that fill the universe, one stands apart. One does something that no other field does, and without it, the universe as we know it could not exist. No atoms, no molecules, no stars, no planets, no chemistry, no biology, no you. This field is the Higgs field. And to understand why it matters, we first need to understand something that seems like it should be simple, but turns out to be deeply strange. What is mass? You know what mass feels like. When you pick up a bowling ball, it's heavy. It resists being moved. When you try to push a car, it barely budges. When you throw a baseball, it takes effort to accelerate it. This resistance to being accelerated, this stubbornness of matter, is what physicists call inertia. And mass is the measure of inertia. The more mass something has, the harder it is to accelerate. The more force you need to change its motion. This is Newton's second law. Force equals mass times acceleration. The more massive an object, the more force you need to produce the same acceleration. But here's the question that Newton never answered, and that nobody could answer for over 300 years. Why do particles have mass in the first place? Where does mass come from? Why does an electron have mass? Why does a quark have mass? Why isn't everything massless, zipping around at the speed of light? Because that's what would happen without mass. Photons are massless, and they travel at the speed of light. Always. They can't slow down. They can't speed up. They can't stop. From the moment they're created to the moment they're absorbed, photons move at exactly 300,000 kilometers per second. If electrons were massless like photons, they would also travel at the speed of light. They could never slow down. They could never be captured by a nucleus. They could never form atoms. And without atoms, there would be no chemistry, no molecules, no matter as we know it. The universe would be a featureless soup of massless particles racing around at light speed, never combining, never building, never creating anything complex. Mass is what allows structure to exist. Mass is what allows atoms to form, molecules to bond, stars to ignite, planets to coalesce, and life to emerge. Mass is not just a property of matter, it is the property that makes matter possible. So where does it come from? The answer was proposed in 1964, independently by several groups of physicists. The most well-known names associated with the idea are Peter Higgs, a British physicist working at the University of Edinburgh, and François Anglais and Robert Brute, working in Brussels. They propose that the universe is filled with a field, now called the Higgs field, that interacts with certain particles and gives them mass. The Higgs field is different from every other field we've discussed in one crucial way. Every other quantum field, the electron field, the quark fields, the electromagnetic field, has a value of 0 in its ground state. When nothing is happening, when no particles are present, these fields are at 0. They fluctuate around 0 because of quantum uncertainty, but their average value is 0. The Higgs field is different. Its ground state value is not 0. Even in the emptiest, coldest, most remote vacuum in the universe, the Higgs field has a non-zero value. It is always on. It is always present. It pervades every point in space at a constant, uniform, non-zero strength. Every cubic centimeter of the universe, whether it's inside a blazing star or in the frigid void between galaxy clusters, billions of light years from the nearest speck of matter, contains the Higgs field at this constant background value. This non-zero background value is what gives particles their mass. Here is how it works, described in terms of its physical consequences rather than the underlying mathematics. Imagine you're trying to walk through an empty room. Nothing impedes you. You can move freely in any direction at whatever speed you choose. Now imagine the room is filled with a thick, invisible syrup. As you try to walk, the syrup resists your motion. It clings to you. It slows you down. The harder you push, the more resistance you feel. You can still move, but every change in your motion requires more effort than it would in an empty room. The syrup hasn't added anything to you physically. You haven't gained weight in the traditional sense, but your effective mass, your resistance to acceleration, has increased because of your interaction with the medium filling the room. The Higgs field works somewhat like this syrup, though the analogy is imperfect. Different particles interact with the Higgs field with different strengths. Particles that interact strongly with the Higgs field have a lot of mass. Particles that interact weakly have little mass. And particles that don't interact with the Higgs field at all, like photons, have no mass whatsoever. The electron interacts with the Higgs field, but only weakly. This gives the electron a small mass. The top quark, the heaviest known fundamental particle, interacts with the Higgs field very strongly. This gives it an enormous mass, roughly 340,000 times the mass of the electron. The difference in mass between an electron and a top quark is entirely due to the difference in how strongly they interact with the same field, the Higgs field that fills all of space. Photons pass through the Higgs field without interacting with it at all. The Higgs field is invisible to photons. It might as well not be there. This is why photons are massless and travel at the speed of light. They move through the Higgs field as if it doesn't exist. Neutrinos barely interact with the Higgs field, which is why they have extremely tiny masses. So small that for decades, physicists thought neutrinos were completely massless. It wasn't until the late 1990s that experiments confirmed neutrinos do have a small but non-zero mass, meaning they do interact with the Higgs field, just very weakly. Now, here's something important to clarify. The Higgs field doesn't literally slow particles down the way syrup slows a ball. Particles with mass don't move slower because of drag or friction. They have inertia. They resist changes to their motion. This is a subtle but crucial distinction. A massive particle at rest stays at rest not because something is holding it in place, but because it takes force to accelerate it. The Higgs field doesn't create friction, it creates inertia. It gives particles the property of resisting acceleration. How exactly a non-zero background field creates inertia is one of the deeper aspects of quantum field theory, and it involves the way the particle's quantum field interacts with the Higgs field at every point in space. The interaction effectively changes the way the particle's excitation propagates through space, making it behave as though it has mass. There's another important point that's often misunderstood. The Higgs field explains the mass of fundamental particles, the elementary building blocks like quarks and electrons, but most of the mass in your body doesn't come from the Higgs field. About 99% of the mass of a proton or neutron comes not from the masses of the quarks inside it, but from the energy of the gluon field that binds those quarks together. The 3 quarks inside a proton have a combined mass that accounts for only about 1% of the proton's total mass. The rest is pure energy. The gluon field inside a proton is incredibly dynamic. Gluons are constantly being exchanged between quarks, creating a roiling storm of field energy. That energy has mass according to Einstein's famous equation E equals mc squared. Energy and mass are equivalent. The tremendous energy stored in the gluon field inside every proton and neutron is what gives ordinary matter most of its heft. So the Higgs field gives quarks and electrons their fundamental masses. And the strong nuclear field, the gluon field, provides most of the mass of protons and neutrons through the energy of its interactions. Both are field phenomena. Mass, that most tangible and familiar property of matter, the thing that makes a rock feel heavy and the ground feel solid, is entirely a product of fields. There is nothing else behind it, no hidden substance, no secret ingredient, just fields interacting with fields. For decades after the Higgs field was proposed, there was no direct evidence that it existed. The theory was elegant and it solved real problems. It explained why the W and Z bosons, the particles that carry the weak nuclear force, have mass while the photon does not. This was a critical puzzle because without the Higgs mechanism, the equations of the weak force predicted that its carrier particles should be massless, just like the photon. But experiments had shown that W and Z bosons are extremely heavy, roughly 80 to 90 times the mass of a proton. The Higgs field explained this discrepancy beautifully. The W and Z bosons interact strongly with the Higgs field, gaining large masses, while the photon doesn't interact with it at all and remains massless. The theory worked. The mathematics was consistent, but direct proof was missing. If the Higgs field exists, then like every other quantum field, it should be possible to excite it, to create a vibration in it, a particle. That particle is the Higgs boson. Finding the Higgs boson would confirm that the Higgs field is real, that it fills all of space, and that the mechanism it provides for generating mass is correct. The problem was that creating a Higgs boson requires an enormous amount of energy. The Higgs boson has a mass of about 125 billion electron volts, roughly 133 times the mass of a proton. To produce it, you need particle collisions with enough energy to excite the Higgs field to that level. And even when you have enough energy, Higgs bosons are produced extremely rarely. For every billion proton collisions at the right energy, only a handful produce a Higgs boson. And once produced, the Higgs boson decays almost instantly in about 1.6 times 10 to the power of minus 22 seconds. That is so fast that the Higgs boson never travels more than a fraction of the width of a proton before it disintegrates into other particles. You can never detect a Higgs boson directly. You can only detect the debris it leaves behind and work backward to infer that a Higgs boson must have existed for that fleeting instant. Building a machine capable of producing and detecting the Higgs boson was one of the greatest engineering achievements in human history. The Large Hadron Collider at CERN, near Geneva, Switzerland, was designed specifically with this goal in mind, though it serves many other purposes as well. The LHC is a circular tunnel, 27 kilometers in circumference, buried about 100 meters underground. Inside this tunnel, two beams of protons travel in opposite directions at 99.999991% of the speed of light. Superconducting magnets cooled to minus 271.3 degrees Celsius, colder than outer space, keep the beams on their circular path. At 4 points around the ring, the beams are steered into head-on collisions. Each second, roughly 600 million proton collisions occur. Massive detectors the size of apartment buildings surround each collision point, recording the debris from every crash. The search took years. 2 enormous detector experiments, called ATLAS and CMS, each involving thousands of physicists from dozens of countries, analyzed trillions of collisions. They were looking for a specific statistical signature in the data, a tiny excess of events that could only be explained by the brief existence of a Higgs boson. On July 4th, 2012, CERN announced the discovery. Both ATLAS and CMS had independently found a new particle with a mass of about 125 billion electron volts. Its properties matched the predictions for the Higgs boson with remarkable precision. The discovery was announced at a packed press conference in Geneva that was streamed live to physicists around the world. Peter Higgs, then 83 years old, was in the audience. He wept. He pulled out a handkerchief and wiped his eyes as the room erupted in applause. 48 years after he had proposed the field that bears his name, the particle that confirmed its existence had finally been found. In 2013, Peter Higgs and François Englert were awarded the Nobel Prize in Physics. Robert Breux, who had worked with Englert on the original theory, had died in 2011, just a year before the discovery. The discovery of the Higgs boson confirmed that the Higgs field is real. It fills all of space. It has a non-zero value everywhere. And it gives fundamental particles their mass through their interaction with it. The standard model of particle physics, built entirely on the framework of quantum fields, was now complete. Every field predicted by the theory had been confirmed. Every particle, meaning every field excitation, had been detected. The picture of reality that emerged from a century of theoretical and experimental work was now fully validated by observation. And that picture is this. The universe is made of fields. Let's step back now and take in the full scope of what we've learned tonight, because the implications are staggering. The universe is not a collection of objects floating in empty space. There is no empty space. Every point in the universe is the location of roughly 24 overlapping quantum fields. These fields are not inside space. They are not contained by space. In a deep sense, they constitute space. They are the fabric from which everything is woven. Matter is not fundamental. Particles are not the bottom layer of reality. What we call matter, the solid, tangible, heavy stuff of the everyday world, is made of atoms. Atoms are made of electrons, protons, and neutrons. Protons and neutrons are made of quarks and gluons. And all of these, every electron, every quark, every gluon, every photon, are excitations in quantum fields. Temporary localized vibrations in entities that are far more fundamental, far more permanent, and far more pervasive than any particle could ever be. The fields are the ocean. The particles are the waves. The waves come and go. The ocean endures. Forces are not mysterious influences that reach across empty space. Every force in nature is mediated by a field. Electromagnetism is the exchange of excitations in the electromagnetic field. The strong nuclear force is the exchange of excitations in the gluon field. The weak nuclear force is the exchange of excitations in the W and Z boson fields. Even gravity, though it hasn't yet been successfully incorporated into quantum field theory, is understood in Einstein's general relativity as a consequence of the curvature of space-time itself, which may ultimately turn out to be a field phenomenon as well. Forces are not separate from the particles they act on. They are the same kind of thing. Field excitations interacting with other field excitations. The universe doesn't contain both particles and forces as separate categories. It contains only fields. Some excitations we call matter, others we call forces, but they are all vibrations in quantum fields. Energy is a property of fields. When you heat something up, you're increasing the energy of field excitations. When light carries energy across space, it's field energy propagating as a wave. When a nuclear bomb releases energy, it's field energy being converted from one form to another. The mass energy equivalence that Einstein discovered, E equals mc squared, takes on a new meaning in the context of fields. Mass is a form of energy. The energy of a particle at rest is its mass energy, and mass comes from fields, either from the Higgs field giving fundamental particles their intrinsic mass, or from the energy of the gluon field binding quarks together inside protons and neutrons. Energy, mass, matter, forces, all of it is fields. The vacuum is not nothing. It is the ground state of all quantum fields simultaneously. It has energy, it has structure, it fluctuates, it exerts forces, it shifts atomic energy levels. It may be driving the accelerating expansion of the entire universe. The vacuum is arguably the most important state of the quantum fields because it is the state from which everything else emerges. All particles are excitations above the vacuum. All matter is a departure from the vacuum's ground state. Everything that exists, everything that has ever existed, is a pattern of disturbance in fields whose default state is the vacuum. You are a pattern. Not a thing, but a process. Not an object, but an event extended in time. The atoms in your body are constantly being replaced. Every few years, virtually every atom in your body is swapped out for a new one. The carbon in your muscles, the calcium in your bones, the iron in your blood, all of it cycles through. Atoms come in from the food you eat and the air you breathe, and old atoms leave. You are not the same collection of atoms you were a decade ago, but you're still you. Your identity persists even though your material composition changes. This makes perfect sense in the field picture. You were never a collection of atoms in the first place. You were always a pattern, a configuration of field excitations, a stable, self-sustaining, self-replicating arrangement of vibrations in quantum fields. The specific excitations come and go, just as individual waves on the ocean come and go. But the pattern persists. You are a wave that has been propagating for decades, maintaining its structure even as the underlying field excitations are constantly renewed. This is perhaps the most profound implication of a quantum field theory for how we understand ourselves. We are not made of stuff. We are made of patterns in stuff. And the stuff itself, the quantum fields, fills the entire universe. The electron field that vibrates to form the electrons in your atoms is the same electron field that vibrates in the heart of a supernova, in the atmosphere of a planet orbiting a distant sun, in the furthest galaxy the Hubble telescope has ever photographed. You are connected to the farthest reaches of the cosmos through the fields that constitute you. Not metaphorically, not poetically, literally, physically. The same fields, the same fundamental entities, vibrate in here to make you, vibrate in there to make a distant star. One continuous fabric, stretching from here to the edge of the observable universe and beyond. And you are a pattern woven into that fabric. When physicists talk about the fundamental nature of reality, this is what they mean. Not particles, not atoms, not strings or brains or any hypothetical entity beyond what has been confirmed by experiment. Fields. Quantum fields that fill all of space, that have been there since the earliest moments after the Big Bang, that will persist for as long as the universe exists. These fields are the most fundamental entities that the most rigorously confirmed description of nature we possess has revealed. They may not be the final answer. There may be a deeper layer beneath them. String theory proposes that fields themselves emerge from vibrating one-dimensional strings. Loop quantum gravity suggests that space-time itself has a discrete structure at the tiniest scales. Other approaches suggest entirely different foundations. But none of these deeper theories have been confirmed by experiment. As of today, as of the best science we have, fields are where the trail ends. They are the bedrock. And that bedrock is everywhere. In the space between your fingers, there are fields. In the space between atoms, there are fields. In the emptiest void between galaxy clusters, where no star shines and no particle has passed in millions of years, there are fields. Fluctuating, humming, carrying the potential for everything the universe has ever produced or ever will produce. Every particle that could ever exist is latent in those fields, waiting for enough energy to bring it into being. Every force that could ever act is encoded in the interactions between those fields. The vacuum is pregnant with possibility. What looks like nothing contains the seeds of everything. Think about what this means for how we see the universe. The night sky appears to be mostly darkness, punctuated by points of light. But the darkness is not empty. It is full. Fuller than the stars themselves, in a sense, because the stars are localized excitations in the fields, concentrated disturbances in a small region of space. But the fields extend everywhere, into the darkness, beyond the stars, filling the spaces that look empty with their quiet, ceaseless activity. The universe is not mostly void with scattered islands of matter. The universe is entirely field, everywhere, always, and matter is just what happens when those fields get excited enough to notice. We began tonight by talking about a table. A solid, ordinary table that you could knock on and feel resist your hand. We traced the history of how humans understood what that table is made of, from the ancient Greek concept of atoms, through the discovery of electrons, through the revelation that atoms are mostly empty space, through the quantum revolution that showed particles aren't really particles at all. And we arrived at the deepest answer physics currently has. The table is a pattern of excitations in quantum fields. The quarks in its atoms are vibrations in quark fields. The electrons are vibrations in the electron field. The forces holding it together are mediated by the electromagnetic field and the gluon field. The mass that makes it feel heavy comes from the Higgs field and from the energy of gluon interactions. And all of these fields extend far beyond the table, far beyond this room, far beyond Earth, filling the entire universe. The table is not separate from the rest of the cosmos. It is continuous with it. The fields that make up the table are the same fields that make up the stars. The vibrations are local, but the fields are universal. When you knock on the table and feel it push back, you are feeling quantum fields resisting compression. When you see the table, you are detecting excitations in the electromagnetic field that bounced off excitations in the electron field at the table surface. Every sensory experience you have ever had has been an interaction between field excitations in your body and field excitations in the world around you. You have never experienced anything else. You cannot experience anything else. Fields are all there is. So why do fields exist everywhere? Because they must. A quantum field isn't something that can exist in one place and not another. It doesn't have edges, it doesn't have boundaries, it doesn't thin out or fade away with distance. The electron field at the edge of the observable universe is the same electron field inside your heart. It is one continuous entity. Everywhere means everywhere. Every point in space, every moment in time, every location in the cosmos, whether anyone is there to observe it or not. The fields don't require an observer. They don't require matter. They don't require energy. They are there in the deepest vacuum, in the coldest void, in the most remote corner of the universe that light from Earth will never reach. They were there before the first star formed. They will be there after the last star dies. They are the most permanent, most pervasive, most fundamental things that science has ever discovered. Tonight you learned that what you thought was solid matter is really empty space, held together by forces. That those forces are carried by fields. That the particles making up every atom are really vibrations in those fields. That the fields exist everywhere, at all times, filling what appears to be empty space with ceaseless quantum activity. That even the mass which makes matter feel substantial comes from fields. From the Higgs field giving fundamental particles their inertia, and from the gluon field providing the energy that accounts for most of the mass in your body. And that you, yourself, are not a thing but a pattern. A breathtakingly complex, self-sustaining, evolving pattern of excitations in quantum fields that span the entire cosmos. The universe is not a stage on which things happen. The universe is the happening. Fields vibrating, interacting, creating transient patterns that we call particles, atoms, molecules, stars, planets, and people. All of it emerging from fields. All of it made of fields. All of it returning to fields. What we call reality is the dance of quantum fields across the vastness of space and time. And that dance has been going on since the beginning and will continue long after every star has gone dark and every particle has decayed and the universe has expanded into a cold, quiet emptiness that is not really empty at all. Because the fields will still be there, fluctuating softly in the dark, carrying within them the potential for everything. The next time you sit at a table and knock on its surface, remember what you've learned tonight. That solid feeling under your knuckles is not what it seems. It is not tiny balls of matter packed tightly together. It is quantum fields, resisting, vibrating, interacting. The same fields that fill the space between the stars, The same fields that existed before the Earth was formed. The same fields that will endure long after our sun has died. You are knocking on the fabric of the universe itself, and the fabric is everywhere. Thank you for joining me on this journey into the deepest nature of reality. If you found this exploration valuable, a like or subscribe would help me keep making these deep dives into the mysteries of the cosmos. And remember, the next time you look out at the night sky and see darkness as between the stars, you are not looking at emptiness. You're looking at fields, the same fields that make up your body, your world, and everything that has ever existed. The universe is not mostly empty. It is entirely full of fields, full of potential, full of the quiet, invisible, magnificent fabric from which all things are woven. Good night, and may you never see empty space the same way again.